In today's video, we will explain how to calculate instantaneous velocity from instantaneous acceleration, and then instantaneous position vector from instantaneous velocity. We shall restrict our discussion to one-dimensional motion. Now, in our previous video, when we calculated the instantaneous velocity and acceleration from the position vector, we had to do successive differentiation of that position vector. And now, since we have to do things in the reverse order, namely from acceleration, we are going to find the velocity and then going to find the position vector, we will have to do integrals. We have to integrate functions with respect to time. So the independent variable here is time. Now let's recall this expression that we have learned before, namely the instantaneous acceleration is the time derivative of instantaneous velocity. This means the velocity, the instantaneous velocity, is given by an integral of the acceleration vector with respect to time. So in order to find the instantaneous velocity, all we have to do is to solve this integral. But one thing about this integral to note is that this integral does not have any limits. No lower limit nor upper limit. So once we integrate this function, therefore, we have to accompany this result of this integration, let's say it's a vector function ft, with an integration constant. In this case, it's going to be a constant vector v0. Only once we have found this vector v0, we have a complete description of the instantaneous velocity. Now, how do we find this vector v0, the integration constant? Now, to do that, we need initial condition. Initial condition is a condition that gives the value of that instantaneous velocity at a particular time, say t0. Now, let's say the value of the velocity at time t0 is a vector, let's call this vector vector A. Then by substituting this result in the solution, we have vector A equals the vector function ft evaluated at t0 plus v0. So since we know what vector A is and we know the value of the vector function f at t0, we can solve the integration constant, which is the constant vector v0. And by solving v0, we have a complete description for the instantaneous velocity, namely the velocity at any time t. We will explain these steps in detail using solved examples next. So in this example, you're given the acceleration of a particle. The expression is 5t I hat. The particle's velocity at t equals to 2 seconds is given to be 17 I hat in meter per second, and we are to calculate the velocity at t equals to 6 seconds. So the condition that the velocity is 17 I hat at t equals to 2 is the initial condition. As we have seen before, this is the definition of instantaneous velocity. So let's substitute the expression for the acceleration, 5t dt. Do not forget the I hat here, because it's a vector. Now the integration is a simple one, and it will give you 5 over 2 t squared I hat plus an integration constant, which we are to determine. Now we are told that at t equals to 2 seconds, the velocity is 17 I hat in meter per second. So substituting this initial condition in the solution just found, we see that v at 2 seconds equals 5 over 2 squared I hat plus v0. Now we know the value of velocity t equals to 2. It is 17 I hat. And now solving for the integration constant, we obtained 17 I hat minus 10 I hat, which is 7 I hat meter per second. So that is the integration constant. Now, having found the integration constant, the general expression for the instantaneous velocity can now be written as 5 over 2 t squared plus 7. So together it's I hat in the unit of meter per second. Now this is the expression that we will use to figure out the velocity at t equals to 6 seconds. At t equals to 6 seconds, the value of the velocity is given by, as shown, by substituting t equals to 6 in the expression just derived, we get 90 plus 7 I hat meter per second. So the complete velocity, the value of it is 97 I hat in the unit of meter per second. So that solves this problem. Example 2. An object's acceleration in meter per second squared is given by this expression right there. It is at rest at the origin. So that's important, at rest at the origin. So we know the velocity and the position at t equals to 0 seconds. So these are the initial conditions for this problem. First, find the position and velocity of the object as functions of time, and then calculate the maximum velocity the object attains. So first let's calculate the general expressions for the velocity and position. We'll start with velocity. So to find the velocity, we need to integrate the given expression for the acceleration. So that's the definition of it, which after substitution for the acceleration function yields the following. Do not forget the j hat as always. And the result for this integral is 1.9 over 2 t squared minus 0.12 over 3 t cubed. Again, this is a vector function plus an integral constant. Let's call this integral constant u naught. Now we are told that at t equals to 0 seconds, the object is at rest. So that means v is 0. Now utilizing this in the expression just derived, we get v at time equals to 0, which is 0, equals 1.9 over 2, 0 squared, minus 0.12 over 3, 0 cubed, plus, do not forget the j hat, plus u naught. So that means immediately we see that the integration constant u naught is a null vector, so it's 0 as well. So that means the general expression for instantaneous velocity for this object is quite simply 0.95 t squared minus 0.04 t cubed j hat in the unit of meter per second. So this is the velocity of the object as a function of time. Next, the position as a function of time. Now we know that the position vector is given as the integral of the velocity with respect to time. Now since we have found the velocity and it's given by 0.95 t squared minus 0.04 t cubed dt. Now don't forget the j hat, and the result of the integral is given by the following. Now note that there's an integration constant, which is a constant vector r naught, and we need to figure that out before giving a general expression for position vector as a function of time. So let's proceed to calculate what r naught is. Now we are also told that at t equals to 0 seconds, the object is at the origin. That means the position vector, the r is 0. And we shall use this information to figure out what the integration constant is. Substituting this initial condition in the expression for rt that we derived above, you get when t is 0, we know the answer is 0, so it's 0.95 over 3. 0 cubed minus 0.04 over 4, 0 power 4. So together, we have a j hat there, plus r naught. So that immediately tells you that the integration constant r naught is 0, which means we can write down the general expression for the position vector as a function of time as follows. And it's given by the following expression. Again, note the j hat and the unit is meter, because it's a position vector. The part B of this problem asks you to calculate the maximum velocity the object attains. Before proceeding, let's explain a little about the maximum and minimum conditions from calculus. So assume y is a function of x. To determine the maximum value of y, you first need to determine the value of x that makes the y maximum. So the condition that enables you to do that is the following. dy dx is 0. By equating the derivative, the first derivative of y with respect to x to 0, and solving the value of x, let's say the value of x that makes the derivative of 0 is x naught, and by substituting this x equals to x naught inside the function y, so the value of y evaluated at that value of x will give you either a maximum or a minimum value for y. Now, which one is it? Now, if the value of y is maximum for x equals to x naught, then the second derivative of y with respect to x evaluated at x equals to x naught will be a negative number. So that means the y is maximum. If the second derivative of y with respect to x evaluated at x equals to x naught is a positive number, then the value of y evaluated at x equals to x naught is minimum. It's that simple. So to find the maximum value of velocity, we need to do those steps to this function vt. But the derivative of v with respect to time is our acceleration, which we know what it is. So we are given that expression. The acceleration function is 1.9t minus 0.12 t squared j hat. So v is like your y before, and t is like your x before. Now, by equating this derivative to 0, or by equating the acceleration to 0, you can figure out the time for which the velocity is maximum or minimum. So that would give you essentially this. Now, the left-hand side can be factorized. Take the t out, so you get 1.9 minus 0.12t, and that is 0. The solution t equals to 0 is trivial. The non-trivial solution is t equals to 1.9 over 0.12 seconds, which is 15.8 seconds. Substituting t equals to 15.8 inside second derivative of velocity gives you minus 1.9, which confirms that v is indeed maximum at 15.8 seconds, and the value of that maximum velocity is given by the following, which is 79.4 j hat in the unit of meter per second. I hope you find the content of today's video useful. If so, please consider subscribing to this channel. Have a great day, and thanks for watching.